All right, everybody, welcome back. This is video number 3 from section 10.14 of AP Calculus BC, finding Taylor or Maclaurin series for a function. Should be our last video if everything works out all right. We're going to pick up right where we left off, where we're finding Maclaurin series for more complicated functions based off of the common Maclaurin series that we've learned about in the first 2 videos. So here we go. Example C. We're going to find a Maclaurin series for 3x times the natural logarithm of the quantity 1 minus 2x. And we start with our common series for the natural log of the quantity 1 plus x, which is just equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc., etc. And my general term is negative 1 to the n minus 1 times x to the n over n. All right, so there's our starting point. Now, we're going to break this down. We're first going to find the series for natural log of the quantity 1 minus 2x, and then once we've found that, we're going to incorporate the 3x by just multiplying that series by 3x. So here we go. The natural log of 1 minus 2x, all we're doing is we're replacing the plus x with a minus 2x. So everywhere where there is an x, we're going to replace it with a negative 2x. So we'll make that substitution straight through. Oops. And with the negative 2x, what I'm going to do is in general term here, is I'm going to turn that into negative 1 to the n x to the 2 to the n x to the n. Negative 1 to the n, 2 to the n, x to the n. All over n. All right, so there's my general term now. Okay, so proceeding from here, what happens, well, let's just go ahead and we'll multiply by the 3x, and then we'll talk about what happens. So we're going to multiply this by 3x to get our series for 3x times the natural log of the quantity 1 minus 2x. So that's going to give us negative 6x squared minus, and when we work this out, this is 4x squared over 2, so that's 2x squared times 3x, so that's going to be 6x cubed. And then when we expand this out, that's going to be negative 8x cubed over 3, which we're going to multiply by 3x. So we've got negative 8x cubed times 3x, which is negative 24x to the 4th over 3. So that's just going to be negative 8x to the 4th. And when we expand this out, we've got minus 16x to the 4th over 4 times 3x. So that's going to turn into minus 12x to the 5th. So on and so forth. And then we're going to multiply this term by 3x. So it turns into negative 1 to the n minus 1 times negative 1 to the n times 2 to the n x to the n plus 1 times 3 all over n for our general term. Now, the one thing that I would like to do is I'd like to, multiply these out, the negative 1 to the n minus 1 and the negative 1 to the n. When I multiply these out, because of the way that my terms are generated, we always end up with a negative 1. Because if I multiply these two together, I've got the quantity negative 1 to the 2n minus 1, which for all values of n is going to be an odd number. So I'm going to go ahead and just get rid of these. I'm not going to rewrite everything, but I'm going to get rid of these and replace them with a single subtraction at the beginning of this term. All right, and so there is our, I need to stretch my ellipsis out a little bit here, but there we go. Our general term is the opposite of 2 to the n, x to the n plus 1 times 3 all over n. Now, interval of convergence. The interval of convergence is not impacted by the 3x. The interval of convergence for the original series is negative 1 is less than x is less than or equal to positive 1. So the IOC for natural log of 1 minus 2x, we're going to substitute negative 2x in here in place of x. And we're going to go ahead and solve this inequality. And when we do that, that gives us 1/2 is greater than x, which is greater than or equal to negative 1/2. And so that is going to be our interval of convergence for this series. All right, next. Example 4, 2x squared e to the negative 3x. We're going to start with the series for e to the x, which is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., all the way up to x to the n over n factorial. And then our series for e to the negative 3x, we're going to replace all of those x's with 3x. And again, since we're replacing them with negative 3x, I'm going to break that down into negative 1 to the n, and then 3 to the n, x to the n, all over n factorial, because that'll be easiest for us to work with our general term here. And now to get 2x squared e to the negative 3x, we're just going to take every term of this and multiply it by 2x squared. So that gives us 2x squared minus 6x cubed plus 9x to the 4th minus 9x to the 5th. And my general term is going to be negative 1 to the n times 3 to the n times x to the n plus 2, all times 2, all over n factorial. And there's my series representing 2x squared e to the negative 3x. The interval of convergence, again, multiplying out here doesn't change the interval of convergence. The only thing that does change the interval of convergence is this substitution. But the interval of convergence for e to the x is all real numbers, and so the interval of convergence for e to the negative 3x is also going to be all real numbers. All right. Cool. So that's how we can build various series representing various functions by using some algebra, some substitution, some multiplication. There's all kinds of things that we can do. Tinker around with some examples and you'll get kind of a handle on how to do a lot of this stuff. In example 2, we're going to write a power series centered at x equals 0 and find the interval of convergence for the given functions by using the fact that these are all geometric series. These are the sums of geometric series. But what we want to do in order to write them as the sums of geometric series, we want to be able to write this in the form a over 1 minus r, since a over 1 minus r was always the sum of our geometric series. So we need to figure out how to write this in the form a over 1 minus r. Well, the first thing I'm going to do is I'm going to look at the constant in the denominator. That's 4. I want it to be 1. So I'm going to divide both numerator and denominator here by 4. And that gives me something that is functionally equivalent to the original function, but it's of the form a over 1 minus r. So we can now identify a is 3, and r here is 3/4 x. And so we can write a series for this. We start with a, then the next term is a times r, then the next term is a times r squared, etc., etc. My general term, if we figure out the general term here, it's just going to be 3 times 3/4 x to the n power. Now, as far as interval of convergence, in order to get this to converge, we need r, the absolute value of r, to be less than 1. And so solving this inequality, we multiply all 3 parts by 4/3. There's our interval of convergence. Now, something you should know, something you'd like to know, is that the interval of convergence for a geometric series, we will never include the endpoints. When we talked about finding intervals of convergence and radius of convergence a couple of lessons ago, we saw that the interval of convergence, we had to test the endpoints. That's not true when we're dealing with geometric series. Geometric series, we always know that it diverges at the endpoints, so we'll never need to include the endpoints in these, and we don't even need to bother testing the endpoints. All right, one more example here. We want to get this into the form a over 1 minus r, so we're going to divide both numerator and denominator by 6. Turns this into 3 over 1 plus 1/3 x. From there we can identify that a is 3 and r is negative 1/3 x. And then we can write our series based off of that. The first term is a, the next term is a times r, the next term is a times r squared, etc., etc. The general term here is going to be a times, oops, I should have written 3, since 3 is my a times r to the n power. And there's a series that represents the function 18 over 6 plus 2x. In order to find my interval of convergence, I'm looking for where the absolute value of r is less than 1. So we'll set up that absolute value, and we'll set up the inequality. Multiply all three parts by -3. And that tells us that the interval of convergence for this series representing this function is from -3 to 3. All right, folks, that takes us to the end of section 10.14. We're going to do a little bit of practice, and then we'll come back next time for the last lesson, section 10.15. We are just about at the end of the course. All right, have a great rest of your day, everybody, and we'll see you next time. Bye-bye for now.